Good morning, friends. In previous lecture, we already derived an equation for heat transfer in fin, and we already discussed the case 1 equation of case 1 for long fin. It is t minus t infinity upon t0 minus t infinity is equal to e raised to minus mx. Now we are moving to case 2. The case 2 is long fin and insulated end tip. So the end tip is insulated by insulation, any insulation, and the length is long. So we are considering x at base x is equal to 0 up to x is equal to L, and the insulation, we are providing insulation, the heat transfer at the end is 0. So we are considering heat loss from the tip is negligible. This is the temperature profile for that case. At base temperature is T0 and at end temperature is TL. In previous case we put T infinitive as the end temperature is atmospheric temperature, but in this case we are providing insulation, so the temperature at the end and temperature of atmosphere is different. So this is the temperature profile for that, and the boundary condition for this case at x is equal to 0, t is equal to t0. So for that theta is equal to t0 minus t infinity, we are putting theta 0 for that. And next one is x is equal to L, the t is equal to TL. Now here theta is equal to 0 as the heat transfer at the end is 0, or we neglect the heat loss from that. So we can say theta d theta upon dx is equal to 0 from the Fourier's law, and we know the equation that theta is equal to c1 e raised to mx plus c2 e raised to minus mx, and applying this both boundary condition in this equation. So applying first boundary condition, x is equal to 0 in both term, we get c1 plus c2, that means theta 0 is equal to c1 plus c2. And applying boundary condition second in this equation, we get theta is equal to 0, so we are putting 0 here, and we are putting L in place of x, so we will get theta is equal to 0, so 0 is equal to c1, and this condition we applied in previous equation of d theta upon dx. So we know that d theta upon dx is equal to m c1 e raised to mx minus m c2 e raised to minus mx. So in that equation we are putting x is equal to L and theta is equal to 0, so we get this equation, and put c2 as subject in that equation, so we get c2 is equal to c1 e raised to ml upon e raised to minus ml, and put the value of c2 in equation number 2, that theta 0 is equal to c1 plus c2, so we get c1 plus c1 e raised to ml upon e raised to minus ml, and by cross multiplication and take common C1, we get C1 e raised to minus ml plus e raised to ml upon e raised to minus ml. So this is equation for theta 0. So we are taking C1 as a subject, so C1 is equal to theta 0 e raised to minus ml upon e raised to minus ml plus e raised to ml. This is the equation for first constant C1, and putting this value in this equation, theta 0 is equal to C1 plus C2, so we will get the equation of C2. So we have two value of C1 and C2 for our second case. Now put these equations or values of C1 and C2 in our previous equation of theta. So we will get theta is equal to theta 0 e raised to ml e raised to mx upon e raised to minus ml plus e raised to ml plus theta 0 e raised to ml into e raised to minus mx upon e raised to minus ml plus e raised to ml. And simplifying this equation, we get this equation theta upon theta 0 is equal to e raised to minus mx L minus x. As we know the base are same in multiplication, we can put like this: e raised to minus m L x L minus x plus e raised to m L minus x upon e raised to minus ml plus e raised to ml. And we know the cos hx or cos h alpha is equal to e raised to alpha plus e raised to minus alpha upon 2. So for this case we can rewrite this equation in form of cos h by using this equation. So we get cos h m L minus x for the numerator, and for the denominator we get cos h m L. And we know the theta is t minus t infinity when theta 0 is equal to t0 minus t infinity. So we get this final equation for temperature distribution of long fin and insulated tip. And from this equation we can also find the equation of heat transfer for the second case. And we also have a third case. It is a short fin. So for short fin, if I draw this diagram, and for that the boundary condition for that is at x is equal to 0 temperature is T0, and at x is equal to L, that we have some temperature which is not equal to atmospheric temperature, but it is larger than atmospheric temperature, and also heat transfer at this end is completely due to convection. So heat transfer at the end we can say Q is equal to QC, and using this boundary condition we can get the equation for this short fin also. So you just try by yourself and get the equation of this. Okay, so we have completed 3 cases for the fin, and we derived the temperature distribution equation for all our cases. Thank you.